So moving away from quantifiers, let's take a look at a specialized technique called mathematical induction, or just induction. Now I say it's specialized, but it turns out to be very useful, and it does turn up in a lot of examples and turns out to be a very useful thing to learn. So let's take a look. Induction. So mathematical induction is a specialized technique for proving statements of the form for all natural numbers n, some statement p of n. So this is the sort of thing that turns up, and you may have seen in the example, the sum I equals 1 to n of I is n plus 1 divided by 2. This is sort of an archetypical example that the sum of the first n integers is given by n times n plus 1 over 2. This is a standard example lots of people learn. But this is an example of what we mean. For all natural numbers n, this statement holds. Now the reason mathematical induction is so useful is, well, A, there are a lot of interesting statements of the form this, but B, it gives us a nice structure for a proof, and it breaks the proof down into two simpler steps. So let's take a look. First of all, there's what's called the base case, which is just proving that the result holds when n equals 1. And then the inductive step, which is proving that if the statement is true for p of k, maybe I'll draw that a little bit more carefully, if the statement is true for p of k, then it is also true for p of k plus 1. So if it's true for the current value of k, it's true for the next value of k. And I always think of induction a little bit like climbing a ladder. The base case proves that we can get onto the bottom rung of the ladder. We can get onto the ladder. And the inductive step says, if I'm at the current rung, I can always step up to the next rung. And putting these two things together tells me that I can get onto the ladder and I can keep climbing up as high as I want. And so if I can show the statement is true when n equals 1, and I can show that if it's true for the current value, it's true for the next value, then it will be true for as far along as I want. So here's an example. For all n, n squared plus 5n minus 7 is odd. Now we could prove this using a proof by cases, but let's prove it by induction. And let's muck around first, do some scratch work to get a feeling for what's going on, and then try to put things together. Okay, well, the base case, okay, induction tells us we have to split our proof into two separate little pieces. So the base case, we just have to check what happens when n equals 1. And that's easy. We have 1 plus 5 minus 7 is minus 1, which is an odd number. So the base case holds. Now the inductive step, let's think about what that's saying. We have to prove that p of k implies p of k plus 1. So we write down the statement p of k, and that's going to imply p of k plus 1. And so proving this implication is true is actually just a little sub-proof inside our proof. So let's continue our scratch work and make sure it works. Okay, so we've written it down here. For all integers, or for all natural numbers k, p of k implies p of k plus 1. So we assume the hypothesis is true. So we assume that k squared plus 5k minus 7 is odd. So it's 2l plus 1. Okay, if we're writing this up carefully, we write, oh, well, l is some integer. And we need to show that the conclusion is true, namely k plus 1 squared plus 5k plus 1 minus 7 is odd. Okay, so expand that out, k squared plus 2k plus 1, 5, da, 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 da. And we can make use of the fact that we know this is an odd number. So we can extract that in there to write this very explicitly as this bit that we already know to be odd plus some other stuff, which just happens to be 2 times something. And so odd number plus even number is odd. Okay, so it makes sense. But we can do this a little bit more carefully. Since we know this is 2l plus 1, we can write this quite explicitly as 2 times an integer, combining what we know about this term here and the stuff left over. So 2 times blah plus 1. And since this is an integer, k is an integer, all of this is an integer, and so this pk plus 1 is true, because we can write this combination as 2 times an integer plus 1. Okay, we still need to stitch these bits together. We've proved the base case is true, we've proved the inductive step is true, but we still have to put it together. So to do that, I'm going to make use of the principle of mathematical induction. I'm going to write this out as a theorem so I can cite it, so I can say, oh, I've done this bit and I've done this bit, so by induction everything holds. So here's what I'll state as a theorem called mathematical induction. For all n and n, let P of n be a statement. So this is just to avoid any sort of weirdness. This is just a sort of setting the scene sort of statement. Let's make sure we're dealing with a set of open sentences which, if I stick in values of n, they actually become statements. They're true or false. Okay, so this is really just a technical requirement. But let P of n be a statement for all values of n. Then if P of 1 is true, so that's the base case, and P of k implies P of k plus 1 is true for all k in n, then P of n is true for all n. Okay, so this now tells us that if I can show the base case is true and I can show the inductive step is true, by mathematical induction, P of n is true for all integers n. It gives us this tool. We can stitch those bits together, say by induction, and we'll be done. But just a little bit of warning here. Many of you, if you have seen induction before, probably saw it in the form of doing simple summation examples. Induction is not adding the next term to both sides. Okay, if you don't know what I mean by that, don't worry. If you've done lots of summation examples already, then you probably have seen, oh, in a summation example, I just add the next term. Induction isn't that. Okay, so I'm going to avoid doing summation examples for a while, specifically to avoid giving that idea. Now, also note that induction doesn't prove everything. Induction is a tool only for things of the form for all n in n, P of n. If your statement doesn't look like this, induction isn't going to help you. Don't fall into this thing, which I guess can be summarized as the law of the instrument. When you have a hammer, everything looks like a nail. Okay? Don't do that. Also, one last thing, if you're going to use induction as a tool for your proof, just tell the reader. You should say, I'm going to use induction, or by induction, blah, 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 holes. Okay, it tells the reader what's happening. Okay, so it's not very hard to put that in, so please do. It helps the person who's reading your work. So let's complete our proof now. So for all n in n, blah is an odd number. Okay, so proof. First thing I'm going to do is say, we prove the result by induction. I'm just alerting the reader to the fact that we're going to do induction, and that sort of describes for the reader what the structure of the proof is going to be. So, base case. When n equals 1, we have 1 plus 5 minus 7 minus 1, which is odd. So the base case is true. And I've even labeled this base case. Now, probably don't really have to do that, but it doesn't hurt to do that, and it does make it easier for someone to follow. Inductive step, right? We assume that the statement holds when n equals k, so k squared plus 5k minus 7 is an odd number, so we can write k squared plus 5k minus 7 is 2l plus 1 for some integer l, and so by expanding out what we need for k plus 1 squared plus 5k plus 1 minus 7 is 2l plus k plus 3 plus 1. And I've skipped a little bit of algebra in here, but I'm going to assume the reader knows how to do a bit of basic algebra, can check it, and probably believes that I've done the right thing. If in doubt, I could put in some more steps around here, just showing how I got to that. But for the moment, this is probably okay. Okay? If in doubt, put in a little bit more work. Don't skip steps like I have here. Now, since l plus k plus 3 is an integer, so I haven't just write this 2 times anything, I've written as 2 times an integer plus 1, it follows that blah is odd. So I've proved the inductive step. P of k, which was this, implies P of k plus 1, which is that. So I've proved the inductive step to be true, and since the base case and inductive step both hold, the result follows by induction. Let's do one more example. So, every natural number n, 3 divides 4 to the n minus 1. Okay, so again, we'll do this by induction. So, base case, when n equals 1, this is easy because 3 does divide 4 minus 1, because 3 divides 3, that's easy. So now we try to do the inductive step. So we assume that this is true when n equals k. So 3 divides 4 to the k minus 1. So we know that 4 to the k minus 1 is 3l. And again, I'm sort of skipping some steps here because this is just scratch work. I know l is an integer. Well, I need to get from that to some statement about 4 to the k plus 1 minus 1. So I jiggle this around to write it as 4 to the k is 3l plus 1. Multiplying that by 4 gives me 4 to the k plus 1 is 12l plus 4. So 4 to the k plus 1 minus 1 is 12l minus 3. And so it's very clearly divisible by 3 because it's 3 times an integer. So all the scratch work is done now. We just need to write it up. So write it up nicely. And it's always a good point when we do write it up nicely to stop and go back and look at our proof and make sure we haven't skipped steps, we haven't made rash assumptions about what the reader knows and doesn't know, and to make sure everything flows nicely. So, proof. We prove the result by induction. We're just alerting the reader to the fact that, hey, we're using that technique. Okay? Base case, when n equals 1, we have 3 divides 4 minus 1, so the result holds. Okay? So the base case is true. The inductive step, assume that 3 divides 4 to the k minus 1. So we're assuming p of k is true. So 4 to the k is 3l plus 1 for some l in z. And again, I've skipped a little step in the middle there, but I'm assuming that the reader will follow along and that I've put in enough information. If in doubt, put in a little bit more. Don't skip that little bit of algebra in between. So then 4 to the k plus 1 minus 1 is obviously 4 times this minus 1, which is 12l plus 4 minus 1, so 12l plus 3, so 3 times this. Again, I've skipped a little bit of algebra in there, but I've done that when I'm writing up the proof, not when I'm doing my scratch work. Again, if in doubt, put in more terms. Don't skip little steps like I did here. Put in some extra words. It's not going to hurt, won't take you very long, and it might help the person reading. But now, since 4l plus 1 is an integer, 3 divides this as required. So by assuming p of k, I've shown p of k plus 1, so the inductive step is true. So now, since the base case and inductive step both hold, the result follows by induction. Now, I'm being a little bit of overkill here. I've said, I'm going to do induction, and hey, it works by induction. I probably don't need to put both of those in, but I should put one of those in. Okay, let's stop there.